slides and solutions. What else? Go back and look at the homework, because I've been known to take old homework problems, some of the easier ones, and put them on the exam verbatim. Go back. If there's anything on the homework you didn't understand, the solutions are all posted. And they're mostly right. They're probably about 95% right at least, but they're not perfect. Because I wrote them several years ago. Op-amps. There was op-amps on the homework. Probably, Jordan, not to the level of what you saw in that quiz today. It's a good review because we don't get enough op-amps in this program. And there really are the workforce of analog engineering. So knowing the basics of them can get you pretty far, knowing the golden rules and things like that. If you want more details on op-amps, 490 in the fall, which I should hopefully still be teaching. Yeah. Got that worked out. Yeah, and that's on. And exam 1, if you have a pre-arranged appointment, you can take it on Tuesday, February 3rd by Zoom. You have to get the appointment this week, just so I don't go nuts with my appointment book, which is getting pretty big. Or you can take it February 24th in person in Frankie 436. You get 2 sheets of notes, those key slides. If you want that information, you need to put it on your note sheet. I'm not going to give you a transform table on the exam. I'm not going to give you the Bodie plot factors on the exam or anything like that, but you can actually shrink them down, keep them at a reasonable size, print them out. I'm fine with that. Things to really study, it's probably in reverse order here. The exam review slides, if there's something you're having trouble with and you don't quite understand, I am always available by email during regular business hours, except for Friday afternoons when I tend to flake off and I'm in lab anyways. The homework, if there's something you want to go back and review, go and look at the homework and the homework solutions. The lecture slides and my notes on them, which are really just solutions for the questions that are on the slides, are in there. They're probably in a much neater handwriting than anything you see with my stylus. And the reading assignments, if you like reading the book, please do that. We've talked about the accelerated master's program. We talked about Tyler Lee. Oh, I just saw this amazing resume today. It was a student. This is how it was laid out. Okay, first of all, name, degree, and a good GPA. And then the next thing that pops out of me is the next thing is skills. And this is kind of what employers are looking for, is that skill set. And then the next thing was a list of projects. Some of them were school projects. Some of them were projects she was working on at home. Some of them were work projects. And then she had a job history. There was a technician job on there. You know, I just wanted to hire her as an intern right then and there. But, you know, everybody's got their own thing on the resume. You don't want to lie about it, but you want to accentuate the skills and the projects. Okay. This is the Bodie plot graph. We've learned that doing Bodie plots in MATLAB is much less painful. And we've also learned that Bodie plots in the real world look mostly like low-pass filters. Yeah. There is an op-amp program problem on the homework that's due on Monday. I think there's 3 problems. The first 2 problems will make more sense after today. The third problem you should already be able to know how to do. And I like op-amps. So look at that. I would look at that problem closely. You may see it again on the exam. I wrote the exam, so now I know what's on it. I wrote it today and yesterday, right? This is where everything comes together. We are going to figure out what we're doing here. It says to skip, but I'm not going to skip it this time. Well, extra day. This is a switching problem, much like this. Jordy's here. This is a switching problem, much like the switching problems we saw at the beginning of the class. It's an RL circuit. And what's going on here is the switch is going to move from position A to position B at time t equals 0. This is an alternative way to solve this with Laplace transforms. First thing I have to do is draw the t equals 0 minus circuit. So it's in position A, because that's where it's moving from. So I've got R in the circuit, and I've got my inductor's been sitting here for a really long time. This is t equals 0 minus. So it's acting as a short circuit. Can't get much easier than that. And this is my IL of 0 minus. IL of 0 minus, it's a series circuit. It's going to be whatever the current source is. So IL of 0 minus equals I0. Okay. When we put that inductor back into the circuit at 0 plus, since we're using Laplace transforms, what we're going to do is we're going to use a model that we're going to use the series model, because when I flip this over to 0 plus, oh, now everybody's here. When I flip this over to 0 plus, I've got a series circuit. So I'm going to choose that one because that will probably be easier. Got a voltage source V0, resistor called R. I've got my inductor will be SL, and it has, in the series model, it has a voltage source in series with it, minus plus, minus is going up, and the value is L times I of 0 minus. So this is simply L times I0. Okay. I can write a KVL equation for that. I got to just assign voltage polarities, plus, minus, plus, minus. Okay, so going around the loop, starting at V0, minus to plus is an increase, it's positive. Plus to minus is a decrease, so minus VR, minus VL, and then this is an increase going from minus to plus, so I've got plus LI0 equals 0. Now we can figure out another piece of information here too. Hold on. Told you it's been a while since I've done this problem. Right. Oh, our solution for our current, we're going to have the same current in the whole circuit. So we're just going to call that I of S. That'll be our variable. V naught minus I of S times R minus I of S times the impedance of the inductor. That's I of S, SL, plus L I0 equals 0. We can do a little bit of algebra here, move all the IS terms to one side. There'll be R plus SL, and what we'll end up with is V0 plus LI0 all over what's multiplying the S terms, R plus SL. At that point, we could put this into standard form. We could draw a Bode plot. And to get it into standard form, it would be V plus V0 plus Li0 over R times 1 plus S. I factored out an R, so this would be L over R and 1 over L over R. And we'd have a pole at 1 over the normal place where the time constant is. Okay. So it's another way of doing it, or you can always go back to that first order equations and just keep it in the time domain. Remember, for our first order RL circuits, we had an equation that worked for every single first order circuit. All you had to do is find I of 0, I of infinity, and the time constant, and plug it in, and you got the solution in the time domain. Either one of those would be acceptable way to do this. And there is the solution. And this is already sticking it back in the time domain. So that's using Laplace transforms. Okay. This is a superposition circuit. I'm going to declare that at this moment. It doesn't look like a superposition circuit because there's only one source. But the thing that makes it into a potential superposition circuit, all the methods you learned in 188 or didn't learn in 188 are still valid. Yeah, okay, are still valid. Now the thing that we've got going on here is we have initial conditions on the inductor. -1 amp is flowing through the inductor at time t equals 0 minus. So when I redraw this circuit in the S domain, I still have the voltage source. It's going to be Vs of S, whatever the heck that is. My resistor, 10/3 ohms, a fractional ohm. Since the back end of the circuit's all parallel, I'm going to put this as a parallel model. So I'm going to use this model of the inductor. We can pick either one. The inductor has an inductance of SL, L's 5, 5S. The current source in parallel with that is a value of, can I read that? I of 0 minus over S. And I of 0 minus was given as -1. So it's -1 over S. We're not going to go through and solve all these. The capacitor is 0.1 farad. So 1 over SC is going to be 10 over S. And with the capacitor, the parallel model has a current source. It's C V of 0. Sorry about this. And C was 0.1, and V of 0 was 5, so this is 0.5 amps. Now it looks like a superposition circuit. Another thing, there's other tricks we could use to solve this. Everything you learned in 188 is still valid. The way I would solve it, the easiest way for me once I got it in this form, is I do a source transformation on the voltage source, make it an all parallel circuit, and once it's all parallel, I can combine the 3 current sources into one. And then I could combine, but the only thing you got to be careful with when you're combining sources or combining impedances, don't combine the source or the impedance you want the information about. Leave that one alone because it will mess up your answer. You won't know what to do with it. Now I could do the superposition circuits fairly easily.
I've got VS, I've got a resistor and an inductor.
And I deactivate the other two sources. Deactivating current sources makes them open. So I would have a circuit that looks like this. I would have another circuit for the first current source. The details are, if you want a neat drawing, they're in the slide solutions. Looks like this, and then I would have a resistor back to now my voltage source is going to be a short when I deactivate that, and I have the capacitor. And then I would have a third circuit, 3 easier circuits to solve. All the techniques you learned in 188 still, or didn't learn, still work here. And, oh, somebody's, there we go. Don't ask me to draw them neither. The extra 2 current sources, that's a good question. When we went through the stuff we went through yesterday, this inductor, if it has energy in it at time t equals 0, and we're trying to put it in the frequency domain, if you solve the differential, if you do the Laplace transform, the Laplace transform comes out looking like something that is an inductor with a voltage source in it that's equivalent or proportional to those initial conditions. And so those are the models that we derived yesterday or last class, whenever that was. So all I'm doing is just applying the models we used in class. The only time you have to add that additional source is when there is energy in the circuit at t equals 0. So for like most of my op-amp problems, I just say there's no energy in the circuit at t equals 0, which means it looks like the 188 model, and these sources go away, and the voltage sources become shorts. And there's a solution. This is the way I recognize the drawings. This is the way Alexander and Sudoku did it in your textbook, and I would have done it differently. A little bit differently, like I showed you. Yeah, I looked at this one. I thought about doing it. Everyone loves Thevenin, don't you? I remember that I hated it. I still hated it when I started teaching it. The only thing I really want to point out here, this is a Thevenin equivalent, and I will, like in 380, I'll do this again and go, yeah, you remember Thevenin. But then I'll actually solve the problems. This is a dependent source, and with dependent sources, we can't handle those really well, so we can't use V Thevenin. The thing that we would do to actually do this is we take out this resistor, and we'd find V open circuit. And then we'd and the other thing we'd have to do would be short out the resistor and find I short circuit. And once we went through all that, we would get our V Thevenin is V open circuit. Our I Thevenin, I don't know what you guys are, is I short circuit, and R Thevenin, or Z Thevenin in this case, would be whatever V open circuit over I short circuit is. I don't know how much of that you're still doing at 188. I think a lot of it got taken out by Dave Scott, and I don't know what you're doing in the lab. But in 380, we'll step you through it. It'll be some simple stuff. Nothing like this. The math on this problem is horrible. Which is why I don't want to do this, because I don't want to confuse you. It is an entire 2 pages of math in my solution. But that's basically what we're looking for. Switch lighting. Okay. This problem I've looked at and I said, okay, I like it. I really want you to learn how to use a current divider, but this circuit doesn't help you learn how to use a current divider because it's too easy to get lost in the math. So this morning I chose to modify it. What we're going to do is we're going to change. This is what happens. Oh, that's Steve, and I'm just going to have to ignore him. Okay, we're going to change this voltage source into a current source. So we're just going to make it I of S. This will make things easier. And we could remove the 1 ohm resistor, but we don't have to, because on the other side of the 1 ohm resistor, the current's going to be the same. They're in series. So this current right here at going into this node would still be I of S. This is an amazing problem. I just realized this is an amazing problem to understand once I modified it. Study for the exam. Okay, so this is a current divider now. The current going in is I of S. If I want to find I1 or I2, these impedances are in series. So I could just call this 4 plus S. And I could call this 2 plus 1 over 2S. And the currents wouldn't change. So I'm okay with that. Just turn them into boxes. Now I've got a classic current divider. And what am I looking for? I'm looking for I of S. We're going to change that to I of S. So what I'm going to do is I'm going to write an equation. I2, this is just the current divider, equals I of S times the resistance, the impedance opposite of I2. So that would be the impedance in this leg, 4 plus S, divided by the sum of the two impedances, which would be 4 plus S plus 2 plus 1 over 2S. Okay, I can read that. What I'm asked to solve for is the transfer function. And engineers use these transfer functions a lot because a lot of the times if you have like a radio system with an antenna, you don't know how strong the signal is going to be coming into the antenna. You don't know what it's going to look like. So you just, yeah.
What is the 2 plus 1 over 2S?
Right here, I combined the 2 ohm resistor with the 1 over 2S capacitor. Yeah. So you don't know what your signal looks like. So what you want to do is you want to just develop a transfer function for it. Then if someone gives you the known input, same thing with like torque speed curves. You don't know what kind of torque you're going to put into the axle, but you want to figure out what speed is as a function of whatever you put in. So these get used a lot. I'm going to have to mute somebody again. Okay. I really, sometimes I wish I had that in real life. Not in class, but I mean, just maybe like in like staff meetings. That would be the place to put it. Okay, so I'm going to combine like terms, and I'm going to move the I of S over. So I've got the, oh, wait. That's not what I wanted. I want, this is the one I want anyways. I2 of S over I of S. Now I know what I2 is in relative to I. In the denominator, there's nothing to combine, except it's not in standard form. In the numerator, I've got 4 plus 2 is 6, plus S, plus 1 over 2S, and I don't really like the improper fractions. So I'm going to multiply both the numerator and the denominator by 2S. It's like multiplying by 1. So I get something like 2S times 4 plus S over 6 times 2S is 12S plus 2S squared plus 1. And I could manipulate that further, get it into standard form and make a Bode plot. Or I could use the initial and final value theorem and find out if the system would be stable at t equals 0 and t equals infinity. A lot of tools I have here now. I could figure out what range of I of S the system would give me a certain range of I2 of S. So these transfer functions get used all over the place. I'll talk about one of their amazing uses at the end. Reason why I don't do convolution intervals. And this is for the other circuit. Okay, so this is a voltage divider. I decided this was not irritating enough. Yeah. What I'm going to do here is I'm trying to find V out over Vn. This is like a voltage game. Oh, this is the last one too. Okay, we're going to skip over to bamboo paper, I think. What I'm going to do is I'm going to do this in two parts. The first thing I'm going to do, let me just show you my philosophy of this. V out, and this is important because I will use this again. I could easily divide that into two parts. I could say, okay, what is VA over Vn? And I could multiply it, and it's a beautiful thing about the S domain. I could multiply it by V out over VA. The VAs cancel out, and I'm left with V out over Vn. So I want to do this in two pieces. The first one is to find VA, and I'm going to use node voltage method for that. Let's just switch over to something I can draw a little bit better in. I figured out how to make a new notebook. I just didn't want to do it in class. This was the exam average in 380. I don't know how that happened. Nobody failed and everyone showed up to take the exam. I was really amazed. Except for the one guy who was getting an emergency root canal. He's taking it this week. I saw his face, he needed it. It's like he looked like a chipmunk on one side. So this is Vn. I have a 1 ohm resistor. I have a 1 ohm resistor. We're going to use node voltage method, and I have an inductor. It's a 1 Henry inductor. I love these values. And a 1 ohm resistor. And this was our VA. And this was our voltage polarity as defined on V out. Okay, so I'm going to use node voltage method. First thing I have to do is I have to define my ground node. And there's a really smart way to do this. You want to put the ground node where it's tied to the most things, because then it becomes a known voltage there. And you also would love to put if I put the ground node on the negative side of my voltage source, I get rid of one equation. So I'm going to put it right there. And once I put my ground node, my predefined 0 volt term there, because ground is, voltages are always relative to something else. This becomes, oh thank goodness, this becomes Vn. So that is one less equation I have to write a node voltage equation for. Next step is to define my current directions. I'm going to say current's coming out of the source, and then it goes down this way and then goes this way. Okay, I've got 3 currents, and once I do the current directions, my voltage polarities, according to passive sign convention, current goes into the positive terminal. And that will, you remember that, it will help keep you from getting a sign error. And I'm going to combine this into 1 plus S and make this a voltage there. Okay, so we've got the The current through the 1 ohm resistor at the top is VN minus VA over 1. That's going in. The 2 currents going out, so that equals VA minus 0 over 1. And on this side, getting to ground, I have a series combination of 1 plus S. So this is VA over 1 plus S. So I'm going to stick, that's an A. I'm going to stick all the VA terms on one side. I have VN over here. Over here I have VA times, it's negative, it'll become positive, 1 plus 1 plus 1 over 1 plus S. Ooh, this is not bad at all. So what do we want? We want VA over VN, is what we decided earlier. We wanted V out over VN equals VA over VN times V out over VA. Okay. I got to clean up this a little bit. I want to put it over a common denominator. We'll just leave this like this for now. VA 2. So this is 2 over 1 plus S. 2 times 1 plus S plus 1 over 1 plus S, which is VA. 2 plus 1 is 3. Plus 2S. Oh, this looks right. Over 1 plus S. So VN equals VA times that. What I was looking for? I was looking for VA over VN. So I would have to flip that fraction over and move it to the other side. VA over VN equals 1 plus S over 3 plus 2S. Okay, that wasn't so bad. Now, we're going to look at the second part of this circuit. And what we want to do here is we want to find my V out over VA. There I can just use a voltage divider. Because if I know VA, V out is going to equal the input voltage, which is right at that node, VA, times the impedance I want the voltage across, which is 1, over the sum of the 2, which is 1 plus S. So V out over VA is 1 over 1 plus S. So I want to take this right here and multiply it by this, and I get V out over VN. V out over VN equals 1 over 1 plus S. Okay. Times 1 plus S over 2S plus 3. I'm just going to change the order. The 1 plus S terms, since they're factors and I'm going to multiply them together, will cancel each other out. And I get this whole thing, I told you this one wasn't horrible, equals 1 over 2S plus 3. I'm not going to give you anything horrible on the exam. If it makes me groan trying to solve it, it will be too long for you. I want to test that you got the concepts down, not that I don't want to test your algebra anymore. I assume you got this far, you can do the algebra. I don't grade students algebra anymore. It's bad. It gives me a headache. I look at your method and see if I think it would work if you make a mistake. Okay, so we've got this transfer function here. Let's look at some cool things we can do with it. Now that we know this, we no longer have to look at the circuit anymore. We know V out is a function of S over Vn is a function of S. I call in 325, I don't know if this is still in the slides, I have transfer functions because sometimes engineers or other engineers, they don't want to know the details of what you did. They just want to plug it into a system diagram and figure out if it's going to work in the system. Okay, what can we do with this? I need my slide. Okay, we want to determine the impulse response. Okay, you get to do this a lot in 348. You get to do this the hard way. The impulse response is what's going to happen if I put a delta function into the system, the delta of t. Let's just go back here. So I want Vn of S, of t, to equal delta of t. Now the really hard way to do this that we're not going to do, and Dr. Rogers let me get away with this, he thought it was cute, to do the impulse response. If I try to do this in the time domain, if I take this and convert this back in the time domain and have this thing in here, it actually becomes this, the mathematics becomes this horrible thing called a convolution integral. I don't do convolution integrals. And I got through my linear systems class just saying, no, there's a trick. I don't know if Fatima will appreciate this or not. She knows I do this too. What you do is I'm going to take Vn of t and I'm going to immediately put it in the frequency domain. So Vn of s, the Laplace transform of a delta function is 1. Okay. Convolution in the horrible convolution integral in the time domain equates to multiplication in the frequency domain. So now I can just take my transfer function and I can do this. V out of S, and I don't see why any sensible person doesn't do this, equals Vn of S times 1 plus 2s plus 3. Vn of S is 1. So that means it's just 1. V out of S equals 1 over 2s plus 3. No convolution integral involved. It's just multiplication. If I wanted to find out what the response was in the time domain, I take the Laplace transform of this, and I'm done. Inverse Laplace transform of that, I'm done. Much simpler than doing the stupid integral. I never learned how to do that. Ji Yang at her interview, her talk was explaining how to do the convolution integral, and for about 15 minutes I could do it. So I thought we should hire her. That was a long time ago. What was the next one? We want to find the response when Vn of t is u of t. Okay, so this is the power. Vn of t is now a step function, u of t. Again, if I try to do this in the time domain, convolution integral. The easy way is to say Vn of s equals the Laplace transform of u of t is 1 over s. So now V out of s is still Vn of s times 1 over 2s plus 3. So now it's 1 over s times 2s plus 3. I could do a partial fraction expansion of that and then take the inverse Laplace transform. Still better than doing the convolution integral. You can see why communications people get mad at me sometimes. I'm almost as much fun with programmers. The response now, I'm going to put an input. I'm going to just change the source completely. I'm going to make it a cosine function, and I want to see what the output's going to look like. 8 cosine 2t. Wow, Jim's going to be happy. 8 cosine 2t. So Vn as a function of t is 8 cosine 2t. Now I have to go to my Laplace chart, which is probably sitting on my desk right now. Oh, I've got notes. This is number 9. This is going to be Vn of s. Normally I'd look at my chart at this point. Is 8s over s squared plus 4. Okay. So if I want to know what my convolution impulse or my cosine response is, V out of s is going to be 8s. This is the power of these transfer functions. S squared plus 4 times 2s plus 3. Again, partial fraction, put it in, no, I don't have to put it in standard form. Partial fraction expansion, then I can take the inverse Laplace transform. If I put it in standard form, I can do a Bode plot and figure out what's going on. This has a 0 at the origin. It's got a quadratic pole somewhere, and it has a whatchamacallit, a simple pole also. So a lot of stuff that you get put together. The point when you understand how all this stuff fits together, you have just become a radio engineer. You've become an analog engineer. That is really all I had for today. We had an extra day. What was that? This looks like an extra thing that I don't have in there. Okay, that was my old notes. Any questions on the homework or anything like that? You can stick around for a little longer.
For which homework?
Any homework, 1 through whatever we've done so far. Hopefully not future homeworks.
I have a question.
Okay.
So I saw the last question for homework 5 about the op-amp.
Right. Oh, yay. That's a good question to ask. Homework 5. Oh, this is, yeah, me, just to fix it. Okay. So this we kind of, yeah, we went through. What is that? I think this is a bandpass filter. Yes. Okay, so what do you want to know about it? Anything in particular or the solution?
Yeah, well, I noticed that it said it had a simple pole at 1,000.
Right.
And a simple pole at 5,000.
Yes.
For some reason, like, because I've done this problem, like I did this problem like 1,000 times, I keep getting simple pole at 100, then simple pole at 5,000.
Okay. Send me your solution and I'll look at your algebra and I'll look at my algebra. It's possible that I may have a mistake in here. But yeah, this is a lot of math to go through.
Okay.
Yeah, you just send me a screenshot of your solution and I'll take a look at it.
Oh, and then one more thing.
Yeah.
So same homework for question 3.
Yes.
I noticed that it's
I gotta tell you a funny story. The composite should be shifted down 40 dB.
yeah.
Shape
So
of that curve is right. I was just, I was off by one of my K factors. On the solution, it literally says the composite should be shifted down, which means where I have the 40 dB at the beginning should have really been at 0 dB. Someone turned in a homework one time that was an exact copy of this, and it said, there's a little note that said composite should be shifted down by 40 dB. And the grader flagged it and sent it to me and goes, yeah, this person just copied my solution. And at that point, I got to be a real smart aleck. And I mean, there were things on my solutions that said, this is wrong, see Ben's solution. And, you know, even if the problem was right, and that people would copy that. Okay, I'm sorry. Yeah, it's just shifted down a little bit. The best way to check those two is, again, put them into MATLAB and, you know, re-verify them. I haven't gone through and redone the homeworks in here since 2016. So that's my four year ago self that did that. Yeah, if you have any questions, if you ever find a mistake in one of my solutions, send me an email and I give you bonus points. I did not put, oh, I can tell you that now. I didn't put a Bodie plot on the exam. There's kind of a Bodie plot, but it's not like anything you did on the homework. I've gotten tired of grading them. There's one point where I just say sketch a Bodie plot of this, and it's something fairly simple. Okay. That's what skill I really want you to get out of this. Back in the days of slide rules, and these were amazing tools. And
So,
they still are.
you said Bodie plots are not going to be on the exam?
I'm not specifically giving you a single, there is a Bodie plot on the exam. I'm not giving you a single problem that just says, this is the transfer function, or this is a function in S, sketch the Bodie plot of this, magnitude and phase. There's a circuits problem on there where you get down to the end and I ask you to sketch the Bodie plot of the transfer function you derived. And it's like one pole or 1 0.
Okay.
It's nothing really complex. It's good to do these once. I'm having more and more trouble justifying this as I go along. With MATLAB and everything. You'll get a lot more hands-on with this when we get to the filter lab. In lab 4, what we're going to be doing is we're going to be the first section. We look at a high-pass filter, which is a 0 at the origin and a single pole and a K-factor. And we plot it in MATLAB. We plot it in Multisim. I believe Multisim uses Hertz and MATLAB uses radians per second. And then you do a hand-drawn sketch of this and you compare the 3 of them. That's the first week of lab 4. And then we get in bandpass filters and notch filters and things like that and the rest.
So is it kind of safe to say that on my, I guess, one of my 2 sheets, I can save some room by not doing the Bodie plot key slide?
It depends upon how well you can sketch simple poles and simple zeros. You can do those in your head, or you can remember those. Then I wouldn't need that.
Okay. We'll see.
You'll see. Yeah. Okay. Yeah. Filters. And for this homework, yeah. The op-amp problems are good circuits problems from the S domain. I didn't put anything too complex on there. And I kept the numbers to ridiculous levels, like 1 farad or millifarads maybe. Millifarads or tens of ohms. Can we just roll off on freeze instead of taking the exam is not that bad. I've mellowed over the years. What happened when I first got here, I had been a practicing engineer, and then I was a teacher for a long time. And then I came back and started teaching engineering, and I never used the theory as a practicing engineer. So I'd forgotten it all. So I was really easy the first couple of years. And then I started figuring out, oh, I know how to do this, all the little subtleties and making this a little bit tricky and doing things like that. And my exams got to be horrible for a while. And now I've kind of like swung back as where I'm like dealing with the grad students now. I realize how little you actually know. So I'm going more for the fundamentals. They're not horrible. I just gave an exam in 380 and there's 14 people in the class and 9 of them got A's. But still, you should study for this. There's a lot of material to cover, but I'm not purposely being tricky. I'm not going to purposely give you hard problems on the exam. In fact, I got rid of some things that kind of irritated me grading them because people didn't get them. And if you know the basics and the fundamentals of all this stuff, you'll be okay. When I was teaching, like 4 years ago, I was teaching 325. I just no. You never want to see one of those 325 exams. It won't be so bad, Lane. Yeah, you can get through this. Okay. Anything else? If not, I'm gonna go have pizza night, where we don't eat pizza anymore because nobody will eat in a restaurant. It's become a potluck. With 5 people I still eat with. My goodness.
Oh, I'm going to grad school. And
Life's fun. Who is not here? I guess Taylor Twitchell. I think that's it. Okay. Nice to
What
meet
did
you.
you say I wasn't here?
Yes, you're here now. Okay.
Yeah, I'm here.
If I ever miss you for any reason, just send me an email and I will just put the grade, I'll give you the grade back and give you mine.
Okay, thank you.
I'll see you. Yeah, that is good. We have an extra. Okay, I'll see you.